represent F value, your carrier frequency to much more fine-tuned, and then you have your modulations in the sine wave signals, and then the amplitude fluctuation of it, and either in its raw form without an even distribution for either amplitudes or phase or frequencies. So it's a job of the carrier signal to make sure all of these raw signals are fine-tuned to meet the carrier frequency signal bands. Okay, and that's addressed by using the various modulation techniques that we went through earlier, either amplitude or phase or frequency. And so once you apply the original field into some of these modulation techniques, you end up having a great signal within the carrier band frequency for efficient transmission. Okay, so now this is where the practice part comes in. This is where you actually see how all of the schemes, either whether encoding or modulation, is actually applied within a given application. So here I have some scenarios here where I have to represent a character G and O, uppercase G and O, as a message within at the physical level, using either any of the first three encoding groups that you'd have, the non-rotating to zero, multi-level binary, or the biphase. Okay, and the actual message is good luck, but we really want to look at the first two characters. From DataCom 1, you know by now that each character has at least an 8-bit sequence that it comes with in terms of digital signal, digital data. Okay, so the question is now, what is G? And this is where you go back and look at your the ASCII character conversion chart, so you can figure out the the decimal value of G and its binary sequence that goes with it, as well as the lowercase o. Okay, so we're only looking at the first two characters of the message good luck here. Okay, and keep in mind there are uppercases and lowercase, and they all have different representation or different decimal value or binary representation of them. Keep that in mind at the physical level. That's when you're about to exit into a medium, whether the twisted pair, coaxial, fiber optic, or through the airwave. Okay? So your representation, I indicated representation must include the ASCII. The binary ASCII here is the character itself. All characters on your keyboards or within a keypad for messaging for user data is considered an ASCII. And then so your A, B, C, Ds, your 1, 2, 3, the hashtag non-alphanumeric characters are all ASCII represented, or attempt ASCIIs. So I actually basically mention that and then come up with its binary before you actually apply the signal encoding to them. And I've also attached the conversion chart, the ASCII conversion chart, so you can be able to look at it easily to be able to encode and modulate the signal. So here is your ASCII conversion chart, where you do have your decimal values from 0 all the way up to 127, which basically denotes all the various ASCII characters you'd come across within an electronic system, either a computer or a cell phone or a terminal or television or whatever. These are the ASCII characters that makes them up in terms of its digital representations or within a data form. So we basically have they basically assign a value from a decimal point of view, a decimal, an octal, hexagon, and then the ASCII itself. So when we talk about null, a null is a 0 in decimal, binary is all zeros, and octal 00, of course, for both hex as well. That's a null, it's an empty character where there's no existence of any signal at all. It's practically all zeros. One has got the SOH ASCII. Actually, let's move away from all of this. From the first 0 to 31 bits, decimal values, let's move away from them and look at the one that actually makes sense in most systems. And these are mostly for key transmission needs. If you were to look at acknowledgement, for instance, for other terminals and synchronizations, acknowledgement, escape over here is a good one. What else? Okay, so these are probably the most commonest what I can tell from these ones. But the much more relevant ones are from 32 bits and up. 32 bits is the minimum decimal value for most of the most widely represented characters on various computer boards or electronic devices as far as digital data is concerned. SP space, and space usually has a decimal value of 32. And it's binary. You can easily, from Datacom 1, you should know this, how to convert decimal to binary in 8-bit sequence. So in the 8-bit sequence of 32, it's 001 0000000. So it's you have your 2 raised to the power 0, which is 1, 2, 4, 8, 16, 32, 64, 128. And if you wanted to generate a high bit for a given decimal value, in this case at 32, the only bit within the 8-bit sequence of that character is only going to be the third bit from your left. That needs to be switched on. And when you have there, you do have what you call a space in ASCII character. In a way, you should probably say the ASCIIs are more of the human interpretation, whereas either the decimal, binary, octal, hex are the machine-based representation. Okay. Exclamation signs are 33 in binary, sorry, in decimal, and binary is 001 00001. For the ASCII character of 0, now you have to keep this in mind. 0, the number 0 in electronic form, digital data form, is an ASCII 0, and it has a decimal representation of 48 with a binary of 0011 0001. Okay? Anyway, you can just go through yourself and you're not required to memorize this. I've actually indicated to you in Datacom 1 that these are usually embedded in most electronic devices on a given memory board, memory chip on the board of that system. For the signal to go through and interpret given ASCII character and convert it to its respective binary form for the signal to be encoded or modulated. Okay. Now, going back to that question assignment, you have G, uppercase G, and lowercase o. So uppercase G, on this side, the uppercase from 65 going. So we have uppercase G, 71. And lower cases are on the other side, which are the higher end of the decimals. And lowercase o is 111 for decimal, and binary is 011011111. I'm hoping you can easily do a conversion if you go back to the DACOM 1 data conversion, okay, from decimal to binary. So let's note those binaries and then use that. So here you have the ASCII character uppercase G with its decimal value and a binary representation as well. And then you do have your signal encodings. I'm just using Excel for these to just make it look much neater and and uh, and presentable. If you're also trying to come up with these or saw some of these signal encoding graphs or sketch some of those graphs, try to use Excel to do it as well. Freehand sketch is not gonna be, it's not that great. Use Excel, be professional about it. Try to sketch it out with the right tool so you can have a clearer view of what it is that you're doing. Okay, indicate your y-axis and then your x-axis. And so here I'm going to probably indicate the the high voltage levels or voltage pulses as a +5 here, a 0 voltage at the level, and then for the multi-level, it will probably drop down to a -5 at the bottom. Okay, so a +5 voltage wise, a 0 voltage, and a -5 voltage. Okay, so keep that in mind. Okay, you have your y-axis and then your x-axis. Please use Excel. Do not use your free hand to sketch it in your assignments. Please don't do that. Use Excel. Know how to manipulate using borders to generate the various signal levels that you have for the various bits. Okay, so for the non-return to zero level, as we've indicated, you can go back to the rules that applies to them. We have zero should have when you have a 0 bit, it should have a high voltage pulse. Okay, indication. A 1, a level voltage pulse. 0, as usual, high, 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 and 1s or lows. For the non-return to 0 inverted, you'd have 0 having a level voltage pulse, as you probably expect it to be for indication of no voltage presence. And then L1 would have a high start, and you refer to your transitions. You transitions from 0 to 1 and 1 to 1. Okay, transitions only happens when you have 0 to 1 or 1 to 1. Any other bits changes does not require a transition. So in this case, we're moving from 1 to 0, no transition, we just stay at the exact high voltage pulse all the way across from 0 to 0 and 0 to 0 again until we have a 0 to 1. That's where we transition. So now a level voltage pulse, you have a 1 to 1, you transition again, from a level to a high voltage pulse. 1 to 1 again, you transition again from a high voltage pulse to a low voltage pulse. So just apply the rules, and that should give you the signal representation for the non-return to zero inverted. For the bipolar AMIs, you do have your zero representing the absence of voltage pulse. So it's leveled, and keep in mind this is where you have the multi-level, right? Where you have the 3 levels of signal representations. Okay, and at the bipolar AMIs, you only transition and alternate on the ones and not at zeros. Zeros always remain level. So in this scenario, you have a level for voltage on for a 0 bit, a 1 for a high voltage, a positive voltage level, a 0 obviously level, and now the next one needs to have an inversion or an alternation, from a positive to a negative, because the previous one was positive, so it means the next one should be a negative, and then another one a positive, another one a negative. So we're only alternating from positive and negative on the ones that we have. And then the pseudotenor, it's just about the opposite. You're only going to transition and alternate on the zeros, whereas the ones remain level. Okay, so if the initial bit was a 0, you do have a plus or high voltage pulse. A 1 is level, so the next 0 should be a negative. So you're now alternating. So a negative, and another 0 again indicates another transition to a positive state. A 0 again, a transition to a negative state, and then all ones are just level. And you do have the Manchesters, okay, with zero bits usually has a high voltage start. The Manchester, the biphase techniques do not have 3 levels of signal pulse representation, of voltage signal pulse representations, but only 2, just like the other ones, besides the multi-level ones. But the only key transitions within these are the mid-bit transitions. Okay. So for the Manchester, you have 0 bit has a high voltage start, or all zeros must have a high voltage start. Okay, so if you notice 0, high voltage start, a 0 here, high voltage start, a 0 here, a high voltage start, and a 0, a high voltage start, a 1, a low voltage start, 1, 1, a low voltage start, and a 1, a low voltage start. Very good. So high, transition mid bit, and the next bit is a 1, so it has to have a low voltage start. And the only way to accomplish that is to just basically move from your mid bit transition to the start of the second bit, which is a 1, and have that level voltage start, or to gain that level voltage start. And then you move in transition mid bit. The next bit is a 0, so you have to move across again to gain that high voltage level signal pulse start. Okay, and you transition mid bit, and the next bit is also 1, so it's a 0, which means that you have to have a high voltage a level start. So the only way to accomplish it by basically after the mid bit transition, you have to move up on the initial or the beginning of the bit to accomplish the high voltage start. If it was just go across, you wouldn't be able to achieve the high voltage start for the 0. Hence the reason why you keep going off. You keep more or less transitioning for the for the zeros and the ones, so you can attain that high and low starts that you need. So that goes across as well. And then your differential Manchester, same approach. It has all the various characteristics that you have. The starting line to indicate it's a differential Manchester, and then you do have your low voltage starts for the zeros um, and the various transition that goes with it. Okay, so that pretty much walks you through how you generate the signal encoding scheme for the ASCII character G, uppercase G, sorry. And I'm going to leave the you guys as your homework. So just practice on that and see how well you can manipulate it uh, to achieve the various signal encoding that's required. Okay, and that should be able to get you by. And if you master that, then you can move on to the entire message itself, which is good luck, and keep in mind all the uppercases involved. The uppercase G, uppercase L, and that's about it. So there are two uppercases, and the rest are all lower cases. So when you're looking them up within the conversion chart, make sure you pick the right decimal value for it, so you can get the right binary and be able to generate the correct signal encoding that's required. Okay, practice, the best way to get it. So in summary, we have some of these key uh, encoding techniques that are adapted for the various signal form that we have, or signal conversion form that we have. From digital data to digital signal, we have the encoding techniques. From analog data to digital signal, we have the pulse code modulation, and then the uh, division multiplexing modulations, or what you have, or whatever you have, or what have you, sorry. And then you do have the digital data to analog signal using the various modulation techniques from uh, uh, the amplitude shift keying, frequency shift keying, phase shift, and then the pulse uh, shift keying. And then when it comes to analog data to analog signal, the modulations are based off the digital data to analog signals, which is the amplitude modulations, frequency modulation, as well as the pulse modulation. Now, a lot of these are coming from the textbook in chapter 5. That's where most of the signal techniques are covered. So if you really want to get a lot more understanding, please do read the chapter 5 of William Stallings, Data and Computer Communication. Any of the version, I'm using the 8th edition, so that should help you get an in-depth understanding. It's voluminous. We can't cover every single thing within just a short period of time that we have, or within the slides. So I advise you to go and read up on that, so you can be much more, or you can get a better grip on some of these things that might, at the initial stage, might get a bit, all over the place, confusing. Like a jumble of information that you can't even visualize or conceptualize. right? You just got to read more and more. Various textbooks have got different approaches to it, but they all have the same basics in terms of just making signal interpretation possible at the various medium levels or application levels. Okay. All right. So that should do it for the signal encoding techniques.